All right, welcome back. Okay, so today we're going to talk about logistic regression models. And I see a question for assignment 2. Yes, you only need to submit the Jupyter Notebook file ended with .ipynb. That's correct, and no need to turn in the CSV. All right. So for logistic regression model, this is model that we I think a lot of the machine learning courses use this one as the first example to showcase how supervised machine learning, the basic practice in supervised machine learning. And I think the model is elegant and has very solid mathematical basis. So it's, and the behavior is also easy to interpret. So, and I think it's also it's fits well with most simple type of data sets that has several features and one output class that is a binary variable. So today we're gonna look at this model, and we basically will talk about how this model is defined. How do we use different types of mathematical tricks to build a model that can do a binary prediction. And I think if we can go smoothly today, then probably we would have time to cover the gradient descent method part for that as well. All right. Okay, so let's think about the binary classification problems. When we use the example of fish classification as the very first, in the very first beginning class, we said if there's salmon versus sea bass that we want to classify, we need to collect a lot of features, right? And we need to, first of all, we need to have a correct label associated with each fish in our bag. Okay, so it's a very typical binary classification problems, and the outputs is a binary variable, which is just 0 or 1. Okay, so it's different. It's different from the linear regression models. In the linear regression model, it's basically a regression model that has a continuous number as the output variable that we wish to predict, like the house price, like the GPAs of students, and it's quite different scenario in binary classes. So the output is not a continuous number, right? It's either 0 or 1. So it's a categorical, and that makes the whole need or the requirements we need to satisfy with a model very different from a linear regression model. So let's look at the fish classification as an example again, but this time we are not using real fish example, but we use the images of fish, and an image typically represented by a matrix of pixels. And basically, we use numbers to indicate the values, the grayscale. For example, if it's a black or white image, we use grayscale number to indicate the pixels. Okay, and what we can do is to take that 8 by 8 pixels, which is 64 numbers, as a very long thin vector to represent that fish image. Okay, so if we have a lot of images, say we have m training examples, then we can stack all these vectors into a matrix, okay, which results in a training example, a training data set X, capital X, that has multiple columns, and each column is a vector that represents one image. Okay, so we will basically use this type of notation when we talk about to define the mathematical notations for logistic regression today. Okay, so what we care about is how we set up the training stage. Okay, because if we borrow the same idea from logistic regression, we are creating a model that will will output some prediction about house price in a logistic regression model, in a linear regression model, and that predicted price is something we need to compare with the actual price, and we will use the difference between the predicted price and the actual price as the cost function. And this cost function is something we want to minimize because we want the model to behave as good as possible, right? We want the prediction from the model to be as close to the actual price as close as possible. So in this case, we are predicting whether our prediction is 1 versus 0, like yes or no, but it's not a price. So this is something we need to figure out how to establish some rules to define this prediction. Yes, so the x1, x2, x3 represent three different images of the same fish. I'm sorry, I need to be gone for 1 minute. Someone's knocking my door. It should be my kids at home. Sorry about that. All right. Okay. It's going on pretty good. Yeah, we have 2 Zoom sections going on in the house, and a 6-year-old and 3-year-old wandering in the house. It's really messy. Anyway, I got it under control. So Brandon, the CX, present different training examples. Yeah. Each indices, like you see the x1, the lowercase x1 with this 1 in the brackets. This 1 means this is the first example, second example, nth example. Yeah, basically the same notation we copied from the linear regression. Okay, all right. So let's start with the idea of using linear regression, using the old way of linear regression to fit the data. So for example, those dots, those red dots and black dots in these plots, they represent a data point, okay? So this is one. So if the 0 indicates salmon, for example, but they still, see. So this 0 means salmon, and these 1 with black dots indicates sea bass. Okay, so these 2 kinds of fish, and we have the data available now, and we see that there are 5 salmon, 5 sea bass in our training data sets, and if we plot it within a 2D dimensional with a 2-dimensional space, and assume that we only have one feature. Okay, we only have one x, then it will be like this. So it looks like some data points that we can separate, that we can fit using a linear regression model. So for instance, if we use a linear regression model, which is exactly the same form as the one that we were familiar with, f theta of x, which is just a bunch of theta from theta 0, theta 1, right, times x to indicate whether this is a salmon or a fish. For example, we can use the threshold as the threshold of 0.5. If theta transpose times x is greater than 0.5, then we say it belongs to the class 1. Okay, if it's below 0.5, then we say it belongs to class 0. It makes sense because 0.5 is somewhere between 0 and 5. Right? It naturally makes sense to use the midpoint in terms of the y label as the threshold to make a separation of the data, to make a prediction, right? So if we fit the linear regression, the ultimate model will look like this. Will be indicated by this linear line. Okay, so it looks like it's working, right? So we can, given all the data points, we can always fit a linear model. Okay, but this way is problematic actually. Okay, so for example, if now we have some new data that belongs to class 1, okay, and given this new data, then we need to fit a new model. So now we have to have a new line plotted because given new data sets, the slope will be a new one. Okay, and if you look at the values, the predictive values for these data points, okay, according to the linear model, because all the predicted values, they fall onto the lines, they also fall onto the linear lines. So to these data points here, their predicted values would be these 3 blue dots, and they are below the threshold of 0.5. So which is a misclassification because they are supposed to be 1, but now according to the new model, they are below the threshold. So this is the problem of fitting a linear regression model, okay, to a binary predicting task. So that's why we need a different model. Okay, a linear model may have problems right now, and what we need is something that works better than the linear function. And such a function that we wish to use, first of all, it should output between 0 and 1. Okay, and we basically choose this function. Okay, we don't use the f of theta, the f theta of x in the previous slide, but we use this function. We call it h theta of x, and it is a combination of 2 functions. First, it's a g. G is a function that looks like this way. It's 1 over g of z is 1 over 1 plus e to the power of negative z, e to the power of negative z. Yes. So you will see this function a lot in the future even when we talk about neural networks, because it's a common activation function. And this theta transpose times x, this is just a linear combination, right? It's just the linear combination that are directly used in linear regression. Okay, we use a bunch of parameters theta, compute the dot product between the parameter and the feature vector x. Yes, that's some additional information. ReLU, yeah, ReLU would be something different from this one, from these activation functions. So we call it a sigmoid function, and this sigmoid function, the shape of the outputs of the sigmoid function is always between 0 and 1. Yeah, because no matter how big z changes, if you let z to be an extremely big positive number, this e to the power of negative z would approach 0, and when this one is 0, then the whole function is approaching 1. Okay, but it's always smaller than 1. And on the other side, if z is a very small, is a very small negative number, then the whole output for this sigmoid function will approach 0. So generally, if you plot the outputs of the sigmoid function, okay, it will be a S shape. Okay, on the left half, when the input is smaller than 0, it's always below the output is always below 0.5. And on the right, the outputs When the input is positive, then the output is always above 0.5. Okay, so you will see a very smooth shape of this sigmoid function. Okay, so let's see if we use this one to fit our previous training examples, and it basically, no matter how you change how you increase more, or whether you include more data, for example, we can include more data points to the right, right? But as long as we set the threshold as in between, right? We use this bar as the threshold, and we use the outputs of the sigmoid function to make classifications. Then the data points on the right will always above the 0.5 threshold, and on the left, all the red dots, all the red points, they are always below this threshold, which makes it much more robust model. Okay, it's pretty robust to all the new data sets. Okay, so that's basically why intuitively this new function is a much more suitable choice for this binary classification problem. All right. Okay. So the outputs of this new function, new model function, h theta of x, actually has meanings. Okay, so the outputs of this function, let's call it y hat. The meaning of it is actually the probability of the input data belong to class 1. Okay, it's directly the probability output. Okay, and if we look at the form of this h theta of x, and we use y hat to indicate the probability of as the probability of these data points belong to class 1, and then correspondingly, because there's only two possible outcomes, 1 minus y hat is the probability of this data point belongs to the other class, which is class 0. Okay, this is quite straightforward interpretation of the outputs of the model function of the h theta of x. All right, and when we do the predictions, because those predictions are not likely to be 100% 1 or versus 100% 0. So we would usually use the threshold in the middle. Say, given the data points and our model, according to the computation of our model, the probability is 0.6, for example. And then we say that it's 60% that these data points belongs to class 1. Okay, which is not perfect, but it's a higher probability than belong to the class 0. So that's why we can claim that this input data should belong to class 1. Okay, and this above 0.5 probability actually corresponds to this theta of theta transpose times x greater than 0. And the probability belongs to the probability below 0.5 correspond to the inputs theta transpose times x that's smaller than 0. And this is quite clear relationship, because if you look at the form of this h theta of x, right? Whenever the theta of t, the theta t of x is greater than 0, then if you look at the shape of the sigmoid function, then this item is smaller than 1, right? When this is a positive number, then e to the power of some negative number would be smaller than 1, which means it's above the whole output would be above above 0.5. Okay, And what if the theta transpose times I times x is a positive number? Then e to the power of some positive number would be something that's greater than 1. Okay, which means the whole probability would be lower than 0.5. Okay, so all these corresponding relationships are worth taking a closer look. Okay. Yeah, so in actual scenarios, when the output is exactly 0.5, that is very rare. Okay, so in those cases, the machine doesn't tell any information. So we basically need to make a random guess. And that also indicates that our features are not representative of the task, of the object we want to predict. Okay. Okay. On these slides. Okay. So yeah, we are so we have solved the first technical difficulty, which is to find the correct function to make predictions. Okay, so the next one is to choose the cost function. Right. Remember, the cost function is how we measure the distance between our prediction and the ground truth label. Okay, so can we use the mean square error, which we used for linear regression model here? And the short answer is no, because if we use the form of mean square errors, which means we need to first compute the y hat. So this one is y hat. And we use y hat to subtract y and the raised power of 2, okay? Okay, but it looks good, but now actually the h theta of x, it's a very complex function, okay? And because there is e to the power of something within this h theta of x, and if we use this complex form of function raised to the power of 2, this will make the whole cost function a non-convex function, which means there are local minima, which means the minima we find using gradient descent methods on this cost function will be unreliable because they could converge to local minimas, which are not necessarily the global minima. Okay, so this type of cost function is not suitable for the logistic regression task. Okay, so we will need to use a new cost function. Okay, so we need to we will go through this cost function step by step. It may look very long, very complex, but we will see that it actually makes sense. Okay, so let's see what's the commonplace with the mean square error function. Okay, so what's similar here is that there's a sigma operator, right? It's sums up all the training, sums over all the training examples, and a little bit difference is 1 over n. Okay, it's not 1 over 2n, but this is no essential difference here. And what's really different is inside the summation operator. Okay, so first of all, there's a first layer of brackets, right? This layer of brackets, there's a negative over here. It's the negative of a summation. The first summation is here. It's yi times logarithm of h theta of xi plus the 1 minus yi times the logarithm of 1 minus h theta of xi. Okay, it's quite symmetric, right? So when this is a, okay, let me use eraser here. So when the outside term is y, right? When the outside term is y, then the inside term is xi. When the outside term is y 1 minus y, then the inside term is 1 minus h theta of xi. So it's quite symmetric. And for short, we can use 1 minus y hats, and we can use those y hats to replace the h theta of x, just for a little bit short visualization. Okay, but this is exactly the new cost function we will use. Okay, so we will first show the function here, and now let's look at why we need to use such a cost function. Okay, so we need to consider the purpose of having a cost function, right? The cost function is something that measures that is something that we want to minimize. We want a model that is good. Say, if a model makes a good prediction, then the cost should be small, right? If a model makes bad predictions, then the cost is big. So that's our basic thoughts about cost functions. So in this case, if the ground truth yi is 1, okay, what would happen? If we look at the equations, if yi is 1, then this 1 minus yi is gone, okay? And this one logarithm of 0 is not defined. So, but this one is 0, so this whole right term is gone. What's left is this minus yi times logarithm of y hat. Okay, this becomes the cost function that's left when the ground truth label is 1. And remember, the cost function is something we want to minimize. So we want this cost function to be small. So what would happen if we want this cost function, the negative of a logarithm function, to be small? Okay, and the result is that the y hat would be big, right? Only when y hat is big, then the negative of logarithm y hat would be small, because the logarithm function is a monotonically increase function, but there is a negative flip around. So we need to have bigger values for y hat, right? And which means the y hat will be close to 1. Yeah, we're assuming that there's only m equals 1 in this case. Yeah, because we neglect the sigma operator. So this is what we want, right? Because we have the ground truth to be 1, and of course we want the y hat also close to 1, because this is the right correction to make, the correct prediction to make. And on the other scenario, if the ground truth is 0, and in that case, the first term is gone. What's left is minus the logarithm of 1 minus y hat. So if we want the cost function to be small, then we will need the y hat to be small as well. And y hat will be close to 0, which is exactly what we need. Yeah, you see the connection here? So by minimizing the cost function in this form, we would naturally push our predictions, y hat, close to the ground truth labels that we wish to fit. Yes, I see.
Professor,
yeah.
I have a question.
Yeah.
The second equation, I don't know from where we got my negative sign.
Yeah.
If we put this 0 value and the second equation, it should be 1 minus 0, that is positive.
You mean
it's the initial negative at the start of the sum?
Yeah, this one. Yeah.
This one? Yeah.
Yeah.
Yeah, because y is 0, so this one will be 0.
Correct.
Yeah, and there's a negative sign or outside.
Oh, this is negative is enclosing all together. Okay, got it. I thought it's negative only in the first term.
No, it's a negative of the summation.
Yeah.
Yeah, it's distributed to everything. Yeah. So it's a very interesting organization here. So by minimizing the cost function in this form, we will naturally push the predictions to be as close to the ground truth as possible, right? So this cost function turns out to be what we need. Okay, so in the next slide, we will have a closer look at the relationships. Yeah, so as a cost function, we want it to be an indicator of how correct and or how wrong our prediction is, right? So when our prediction is wrong, then we want a cost function. We want the cost function to give relatively large penalty, right? So, for example, in this case, when the ground truth is 1, and the cost function is the negative of logarithm of y hat, and I also ignore the sigma operators here. All right. So if our y hat is 1, then that means it's a correct prediction. So we should give no cost, right? So if we look at the this plot here, the y is the logarithm of the negative logarithm of y hats, and the x-axis is y hat here. So when y hat is 1, the cost function is really small value, right? Because it's a correct answer. It's close to 1, right? It's not something. It should give no cost, right? And if y hat is 0.75, then it's a close prediction, but there's some error. So we should give some small cost to the model. Okay, so the cost increases a little bit. Okay, so if we made a bad prediction, right? We made a prediction as 0.25, which is the wrong prediction. So we need to give a relatively big cost. Okay, and when y hat equals 0, which means we're making the totally the opposite prediction, which means we need to push forward. We need to push the prediction to the other side. We need to push back, right? So the cost will be infinite. Okay, so this type of cost function is naturally makes sense in our test. Okay, if it's on the other side. When the ground truth is 0 and the cost function is negative logarithm of y minus y hat, then it's basically the same thing. When y hat is 0, that's exactly what we need to predict. Then the cost is small, is 0, no cost. If the prediction is not perfect, then the cost is also a small one. But if the prediction is a wrong one, it's getting towards the other side, the cost will increase really fast. When we are making a totally opposite prediction, then the cost will be infinite value. Okay, it's basically the same case as the previous example. Okay. So you can use these 2 slides to help yourself understand why such a cost function would be exactly the one we need for making a binary predictions. All right. So this type of cost function is just we can think of it as a one-line expression of defining the cost with 2 different conditions. Okay, when we have the ground truth is 1, then it should be something like this. When the ground truth is 0, it should be something like this. Okay, so this one is just a compact form that's combining these 2 conditions. Okay. Do we assume that base 2 are 10? I think in this case, the most used value is the logarithm with base e. Okay, and the e is the base for natural logarithm functions. It's around 2.71 something. Yeah. Okay. And we can given this cost function and the form of model functions, we're able to set up the training pipelines. Okay, so there's actually another way of thinking about the cost function for logistic regression. I think it would be really interesting to if we go through that this probabilistic way of thinking, right? So because the outputs of the logistic models function has meanings. It's the as we mentioned, the outputs of h theta of x is the probability that this data point belongs to class 1. Okay, and one, so that 1 minus h theta of x is the probability of being class 0. Okay, so that's what we have. So if we write these probabilities also in a compact way, then we can write it as this one, h theta x raised to the power of y and times 1 minus h theta of x raised to the power of 1 minus y. Okay, so because if you look at y, when y is 0, then this left term is gone, right? It becomes 1, right? And the right term is 1 minus h theta of x, right? And if y equals 0, then when y equals 1, then the right term would be gone, and the term left is h theta of x to the power of 1. Okay, so if we combine these two equations, we can write it into a compact style, right? So that's how we interpret the model's output from a probabilistic point of view. So given a data set that contains m examples, for example, then we are actually fit our parameters so that the parameters can maximize the likelihood of data. Okay, so what we mean by likelihood, the likelihood is just the probability given the data points. Okay, you explain the syntax of those first two statements again. You mean the here, right? Yeah, okay, I see. So this probability syntax means that the probability that the class of data x should be 1 given the data and given the parameters. Okay, so because that's how we make predictions, it's a conditional probability given the data and given the theta. What is the probability that it belongs to 1, it belongs to 0? It's a probabilistic description of how we use the model to make predictions, because x is the data and the theta is our parameter. Okay, x is the fish and the theta is the ruler that we have. So combining this ruler and the fish, we are making predictions about how likely this fish is a salmon versus sea bass. Okay, so the likelihood of the data is basically the product of all the probabilities of the product of probabilities for all the data points in the data sets. Okay, we this symbol is to multiply all the items together, right? So each item is one probability for each single data instance. and I iterates over 1 to n. Okay, so we simply substitute this term into this likelihood term. Okay, so this is a likelihood, and we want the likelihood to be maximized, right? Because we want the models, we want the thetas to make good predictions. We want the probabilities to be as big as possible. So that's why, given the likelihood, we can apply a logarithm outside the likelihood function, because the likelihood is a product of a bunch of numbers. And we know that if we apply a logarithm function upon a product, it will become the summation of several items, which makes the computation easier. And the exponential, the y's at the exponential positions will be also eliminated, right? So the logarithm of the likelihood function would be like this. Right, now we can see something that's really familiar, right? Because if we apply the logarithm function here, the y hats, the yi will be gone, will be outside, and what's inside the logarithm function is the ht of x, and the y minus 1 minus y will be here, and the 1 minus h theta of x will be inside the logarithm function, right? This is exactly the form of the logistic regression's cost function, right? Without the negative symbol, right? Because we are going to maximize the logarithm, the log likelihood function, which is essentially the same thing as minimize the negative log likelihood, right? So the negative log likelihood function is exactly the cost function that we defined for logistic regression. Okay. So minimizing the cost function is equivalent to maximizing the likelihood of data over our parameter theta. Okay. So that means in probabilistic theories, we are making the correct choice for choosing the cost functions in such a way. And the mathematical reason, the probabilistic reason, also supports the way we. This is the probabilistic reason that supports how we choose the cost function in this way, with the y times logarithm of h of x, 1 minus y times logarithm of 1 minus h of x. The only difference between the cost function and the logarithm function is the negative here, right? We are minimizing the negative log likelihood. It's the same thing as maximizing the log likelihood. Okay, so this is some interesting connection to the probabilistic theories. All right, so now, given the cost function defined, the next immediate step is to use the cost function to compute the gradients. Right? We want to minimize the cost function, so we need to use gradient descent methods. All right. So we basically want to do the same thing that we did for linear regression models, but now we have a new cost function, and we want to find the minimum of this cost function step by step. Okay, so we need to observe the gradients. We need to compute the gradients for this cost function. Okay, so it looks a pretty complex form. So we will need to carefully take the derivatives of this cost function with respect to all of our parameters. All right. Okay, so it's a pretty long term, and if we think about this, the partial derivative of this term inside the sigma, inside the summation operation, it's taking the derivative of this equation with respect to theta. That's what we need to do in order to do gradient descent, right? So we basically split the two parts because it's a negative connection in there. So we remove the most outside parenthesis here. So the adding becomes subtracting, right? Because the negative moved inside. So there are two parts now. We actually want to compute. Now we apply the chain rules of partial derivatives. So hope you still remember the chain rules in calculus. So we want to compute the partial derivative of this logarithm of h theta of x with respect to theta, right? And we know the derivative of a logarithm function, right? So when we take the derivative of a logarithm function, say x inside with respect to x would be x 1 over x, right? So this is the logarithm function, the derivative of logarithm function. So the inside of the logarithm function is h theta of x. So we will first put 1 over h theta of x outside there, and then take the derivative of this h theta of x with respect to theta, and times these two derivatives together. Okay, so that is basically the chain rule, and we do the same chain rules for the right part as well. Okay, so this is the right parts. So maybe a little difference is that there's a negative symbol here, so that's why the negative symbol is there. Okay, but this step makes it makes the whole expression easier, makes the whole expression simpler, because what's left now is just this term. These terms are the same. We just want to know the derivatives of the h theta of x with respect to theta. That's what we need to know. Okay, so from this step to the next step, from this step to this step, we also simplify the h theta of x to y hat. Okay, all right. So the next key computation is what is the derivative of the h theta of xi with respect to theta. Okay, so this is something we're gonna use. We're gonna use the property of the sigmoid function. Okay, because h theta of x is a sigmoid function of theta transpose times x. Okay, so we're gonna use the chain rule again. Okay, because it's h theta of x is a g of theta times theta transpose of x. So we basically decompose the derivative into two parts. The first part is this derivative of the g with respect to z, and we let z to be the theta transpose times x. Okay, it's an intermediate variable. So we know that the derivative of the sigmoid function can be computed in this way. Okay, it's a complex form, but it still can be computed. And we got to use some property about the derivatives with respect to natural exponential function. Okay, but anyway, we can compute the g of z, the derivative, the first derivative. And the second derivative is easier. It's a linear function, right? The linear function, the blue parts, the derivative of z with respect to theta should be the derivative of z with each component of theta, because theta is a vector. We can have multiple features. We can have theta 0 to theta n, right? And the results for each partial derivative here is a corresponding feature, x0, and this one corresponds to the x1, right? and the derivative with respect to theta n correspond to xn. So which means we can write it as x. The derivative of z with respect to theta is x. Okay. So having these two parts solved, if we put them together, it's just the form for this derivative is the product of the two, right? It's e to the power of negative z times x divided by this stuff, right? So if we do split, like make it easier for the computation, we can decompose further into two parts. These are just the mathematical tricks. We have one part outside times 1 minus the same part inside times x. Okay, and then you can work on this on your paper. Actually, it's quite interesting to work from the beginning to the ending term here. So now we need to keep in mind that this is just the y hat, right? Because h theta of x is right here, right? We are actually using the definition of h theta of x, right? We can replace this thing with y hat, and this term is also y minus y hat. Okay, so this derivative, this key derivative, can be expressed by y hat times 1 minus y hat times x, right? And we are done. After we are done with this step, we can plug in these key derivatives to the term in the previous slide, right? Let me go to the previous slide. So the previous slide looks like this one, right? We just need to plug in this term into the derivative of the cost function. So which would give us, right? Which will give us a pretty long term, but we will find that a lot of the terms can be eliminated. Okay, and it turns out to be a quite simple form. It's just the y hat minus y times x. Okay, and y hat is the prediction, and y is the ground truth, and the xi is the feature. That's the partial derivatives. That's the gradients of the partial derivative of the cost function with respect to the theta. Okay, and the complete form, because that's the above form is the form without using the sigma operator, and the complete form should sum up all the data instances and normalized by m. So if we put them all together, then the complete theta will be like this. Okay. So it's actually a very similar form. It's actually a very similar form to the linear regression. Okay. So we can put them together without telling a difference, whether which one is for linear regression, which one is for the logistic regression. So the only difference is how y hats are computed. Okay. So in linear regression, the y hats here is just the linear formation, is a dot product between theta and x. But in logistic regression, the y hats is the outputs of the sigmoid function. Okay, that's the only difference. Okay, but the form of the gradients for logistic regression is the same as for the linear regression. Okay, which also in statistics we would call logistic regression a type of generalized linear regression, because the form is very it's basically the same form of how we compute the gradients. All right, I think from slide 14 to slide 16 are the lot of critical steps of computing the gradients of the cost function for logistic regressions. But I think it will help you better understand it if you work on your paper on your own for all the gradients computation. Okay. It will be really helpful if you make sure that all piece of equations fit together into the final form. Okay. All right. So we're almost there. We can compute the gradients, and then we can use the gradients to update the parameters. So all the gradients descent process is the same, more or less the same as linear regression. Okay, we will initialize the theta. We need to repeat the steps of computing the gradients using this formula, and we need to update the parameters defined by the gradients, also controlled by the learning rate alpha, okay, until we are satisfied. All right, and we are done. We are, after the gradient descents are converged, we can make predictions. Okay, we can use the models trained from this step to make predictions. So given any new data points, x new, for example, we can use the model, the h theta of x, the h theta of theta transpose times x to make predictions. It outputs the probability of y belongs to 1, right? And in a simpler way, we actually don't, if we don't want to know the probability, we can just use the linear combination, theta transpose times x. If it's positive, then we say it's 1. If it's negative, then it's 0. All right. So in statistics, this linear combination theta transpose times x nu has a name called log odds. So it basically is the ratio of the probability belong to 1 versus the probability belongs to 0. Okay. This is just for some connection to some statistical terms. Okay. So now let's talk about how we represent the data in training multiple examples. Okay, so this is some notations that we're gonna stick with in the future. Basically, logistic regression will be the basis for will be the basic building blocks for more complex models. Like neural network, basically neural network-based models are a lot of the simple stack of a lot of the simple models, logistic regression-like models. Okay, so when we talk about training data, like we have M examples, we use the M in the superscripts within the brackets to indicate that each example, and we basically need to stack those examples into a matrix, okay? And the capital X would be n by n data sets. We n by n matrix, and we have n rows, and each row is for a feature, and the m column, and each column is for a data instance. And we also have Ys. Okay, so these may be a little bit a little bit different from the logistic from the linear regression way, right? So in linear regression, we seems to transpose x a bit. X becomes a m rows and n columns, but in order to be consistent or be convenient for future usage in the neural network models, we will stick with this notation. That's all the training instances are, all the training examples comes in columns. Okay, so the labels, the Ys are also a row vector now. It has m columns but has one row, only one row. All right, that's X and Y. So this way is a better for future neural network models. And a second change we want to make for parameters is that we will use a new notations. Instead of theta, we will use W. Okay, W that is a n-dimensional vector, and a b. B is for bias term. Okay, b is just a single variable, scalar variable. So given x, we make predictions. So this is for logistic regression still. Okay, when we make predictions, we use W transpose x plus b instead of theta transpose times x. Okay, and this sigma is for the sigmoid function. Okay, so why don't we use theta? Because in order to use theta, theta transpose need to include the theta 0, right? And the theta 0 is the intercept term for the that we borrowed from the linear regression model. Okay, so the theta 0 term actually corresponds to a dumb feature that has all ones, right? But we want to get rid of this theta 0 because we don't want to change our feature. We don't want to change additional rows as a all one feature. We don't want to do that. We just use a bias term to indicate that parameter, to indicate that theta 0. Okay, so actually b corresponds to the theta 0 and w corresponds to the theta 1 to theta n. Okay, so without using theta, then our cost function would be a little bit different. Okay, so the cost function is with respect to w and b now, and the gradients also have two parts. We have the gradients, we have the partial derivative of j with respect to w, and with respect to the b as well. Okay, so there's no need to create a once in x, and it's also consistent notation with our future neural network models. All right, so that's pretty much for it for the logistic regression, and we have some time left. I think it'll be we can have the remaining slides covered because it's just the simplest case of making binary predictions. But in real world applications, it's very often that we need to make multi-category classes classification problems. We want to tell whether this fish is a salmon fish, or it's a tuna, it's other kind of fish, or it's very likely that we want to make more than just binary predictions. So how do we deal with those multi-class classification problems? Okay, so the example we show here is a well-known handwritten image classification, or we want to predict the customer's choice, predict the traffic directions, right? So for this type of multi-class classifications, we will need to use some technique called softmax regression. Okay, so it's called regression in the same way as logistic regression, but it's still a discrete classification problem, but with multinomial categories, with multiple categories. It's also called multinomial regression. Okay, so if we look at the problem, it basically has k possible values for the outputs y. So the label can ranges from 1 to k. Okay, so it's similar to logistic regression in a way that we need to model the probability given the data point. We need to model the probability of y equals to a certain value of k. Okay, we need to model these probabilities. Okay, so we basically how we do that, we will need to use some model indicated by this HWB of x. So this is similar to h theta, right? But because we use a new notation WB to indicate to represent the parameters, so it becomes HWB of x, and it actually has multiple items. It has k items because we want to not just output prediction, the output for one class, but it's k class. So the output is a vector. And each element is the vector for each class from 1, 2, 3 to k, okay? And how we do that is to compute this quantity. It's E raised to the power of this linear combination, okay? It's the W1 transpose times X plus B1, and E to the power of W2 transpose times X plus B2, and E to the power of WK transpose times X plus B2. So you see the W's has has K set of W's, and the B also has some K set of B's. So, and the outputs here is normalized by the summation of all these E to the power of something, okay? Because we want to normalize the items so that they sum up to 1, so that they are properly defined as a probability, okay? So because we have K set of parameters, we basically have a W and B like this, okay? The W and B's, if we put them into column vectors, they would be a K, a n by k, basically a n by k per a matrix. Okay, we have k set of parameters for each category. All right, and the cost function for submax would be a little bit complex, and we need to use the delta function, which is indicator function. If the statement is true, then this indicator function is 1. If it's not true, then the indicator returns 0. Okay, so the cost function looks like this. If we don't look at this outside sigma, because it's sum up over all the data points, if we just look at the inside, there's an indicator, there's a logarithm function. If we ignore this inside, and it looks actually pretty similar to logistic regression, right? If you remember, logistic regression is y times logarithm y hat, right? Plus 1 minus y logarithm 1 minus y hat, okay? And inside, it's just the summation over 1 to k outputs, okay? And a special case for logistic regression is k equals 2, right? So when k equals 2, it becomes the logistic regression, okay? So it's actually the same formats for logistic regression, okay? And of course, it makes the computation more complex when we want to take the derivatives of this cost function. So the cost function would be like this. So let's go to the next slide. When we take the so this cost function makes sense. So we can think of that when y equals 1, all the other k's are gone. So there's only one item left, okay? So it's actually pushing the y hat towards 1. And when the y equals k, all the other items are gone. There's only a y equals k left. And this probability is pushed towards 1. So the reason behind this cost function is actually similar to the logistic regression model, okay? So for the gradients, it's basically the same form, okay, as the logistic regression. It's just y hat minus this indicator function times xi. And for the gradients with respect to b, there's no x, okay? Or you can say that x is 1 here, okay? All right, so I think these are for some additional knowledge for the multi-class classification problem. It's basically built on top of the logistic regression model. So we don't actually know all about the details of how these softmax regression is computed, how the gradients for softmax is computed, but it's basically the same thought as the logistic regression model. All right. So for the softmax layer as the output in a neural network, this is something we're gonna see in the future after we have covered the deep neural network models. And this is a very commonly used standard techniques in deep learning models. And that's pretty much for today. And I think I can release the homework for logistic regressions, which will be due next weekend. Okay. And if you have questions, you can let me know now. Or you can join the office hours on Wednesday or send me emails. Okay, I see your chats. Let me check quiz today. Yes, there will be a quiz for logistic regression. Yes. All right. Well, we need to know every step of math. So, yeah, knowing about the math would be really a big help for you to accomplish the logistic regression assignments. Knowing about the derivatives for sigmoid function is, I think should be a sort of requirement for this course. Yeah. So you will see a lot of those practices well, especially after we have talked about the neural network. Okay.
Professor, when you were saying that we don't really know how the softmax, how it works with gradient descent, were you just saying like in general right now, or just in general we don't really understand how the softmax regression works?
So I mean, just for now, for example, let me be more specific. So for this page, I showed the equations for how to compute the gradients for a softmax regression model, but how we derive these terms is not shown in this slide, right? So what I mean is that how it's not required to understand how we derive these terms for softmax, because it's a way more complex than logistic regression. But logistic regression is still a requirement.
Oh, okay, thank you.
Yeah. All right, so if there are no questions, I'm gonna stop recording. And thank you for